Pleasure to welcome Anastasia Volovich, who was one of the pioneers of the twistor strings. She managed to put the whole S matrix for Yang Mills on just one line with even twistors. And now she's, but that was
20 years ago.
20 years ago. Sorry, 20 years ago, and so now we're going to see where all that has landed us in the intervening time. So thank you very much.
All right. So first of all, it's great to be here. Thank you so much to the organizers for inviting me. So I'm going to tell you a little bit about some recent developments in N=4 Yang-Mills theory. And I should just start off by saying none of this past decade would have been possible without twistors, and in particular momentum twistors. So all the progress relies heavily on the twistors, so it's very relevant to this conference. Okay, so the outline of my talk. So my talk is going to have 3 parts. I'm going to start with the introduction. This is a twistor conference. Usually I'm used to Amplitudes and more physicist conference. So I'm going to say a little bit about amplitudes, why we're interested in computing amplitudes, and what's been some of the progress in the field, and touch upon the use of twistors in this program. Then I'm going to be a little bit more specific to talk about the amplitudes in N=4 Yang-Mills theory. I'll just give you a status overview and some of the tools we use, and among those tools are momentum twistors. And then I'll conclude with a little bit more technical, and maybe I'll be a little bit quick on that. I'll just so that it's not a review talk, I'll tell you a little bit about what we're thinking about now, and some recent work and some work in progress. So basically the things that I'm mostly excited about. All right, so I'm going to start telling you a little bit about scattering amplitudes. So scattering amplitudes encode elementary particle interactions, and they determine the probabilities of various outcomes. So you have some particles colliding, they interact with one another, and you get some resulting particles. So scattering amplitudes are the most basic observables in fundamental physics. Now, standard model has been tested at the LHC to a very high precision. So the motivation for computing the scattering amplitudes comes from collider physics. And here I have a plot of the standard model production cross-section measurements. And you can see, if you can see in the back, you can see that as the number of the final states go from 2 to 3, the theoretical uncertainty, which is in gray here, starts to grow right here. So that's all you need to take away from this plot. There are lots of things in this plot. But so when the number of final states is 3, then we're talking about 5-point amplitudes. So once we deal with 5-point amplitudes, much less is known about them. And as you see, the experimental arrow is right here, and the ratio of data to theory, this gray becomes higher. And that is because some of those amplitudes have not been yet computed. So that's the motivation, which comes from hardcore collider physics. And another slide, here's a slide from a wish list from the report on the standard model wish list. You can see these are the processes, these are amplitudes, this is 3-point amplitudes, and these are some 5-point amplitudes, and that's what's known, and that's what's desired. This is just to, you don't need to know all the details about this, but this is purely to motivate and just tell you that it is very important to get a handle on those computations. Okay, so, and that brings us to this field of scattering amplitudes, a community of people who do those computations in various theories. And it's been a rich and fast-growing field. So actually, this slide is maybe a couple of months old. If you go to Inspire and you search for scattering amplitudes, you get about 1,000 papers per year. And there are annual conferences. In the past, it started off, indeed, which I'll mention from the twistor string. It's been going on for maybe past, I guess, 16, 17 years, and the number of people doing it has grown. So for example, last year in CERN, we had 423 participants. And it's gotten to the point that in addition to those annual conferences, there are also a lot of programs and meetings. For example, every week you get a choice of an Amplitudes meeting to go to. For example, this week you can be in Florence at the Mathematical Structure of Scattering Amplitudes program, or you could go to Portugal to the conference Amplitudes Meets Cosmology. But I chose to come, I guess, here. So third choice, because I love Cambridge. I always happy to be here. I guess there's a lot of also young and energetic people organizing various meetings. I myself just realized that I've organized 16 weeks of various programs, just this in 2024. So it's just, there's a lot of excitement in this field. The field grew. And although it started with the collider physics, so people wanted to, precisely compute various processes, it blossomed in many directions. So this is from the, so now it's a subfield in high energy theory, and there's a Snowmass report on the whole field. And so this is amplitudes, people do different things. There's string theory, there's integrability, goes to supergravity. Of course, has started with LHC collider physics. People are computing classical gravity and gravitational wave processes. And my interest mostly has been in n equals 4 and in related mathematics. So that's what I will talk to you about today. Before I do that, let me explain to you the goals of this whole program. So lots of people, lots of work, lots of applications. And the goal of this program is a twofold. On one hand, we would like to explore the mathematical structure of those amplitudes. But on the other hand, we want to use that structure to make the previously impossible computation possible. So the success of this program really lies on two pillars. So I stole this from Zvi Bern, who's one of the pioneers of this field. And so on one hand, you really need both pillars. So on one hand, you would like to find some mathematical structures, beauty, symmetry, anything. And then you do want to compute something using those structures. You don't want to just, okay, I found an algebra, okay, cool, but can you do something with this? And especially relevant would be to do something for outside your immediate colleague interests. So to thrive, really, one needs support of both pillars, and on these two pillars, the Amplitudes programs is resting on. Okay, very good. So why am I here? Why am I not in Portugal, not in Florence? So Amplitudes and Twistors. Twistors have been absolutely of fundamental importance in this field. In fact, 20 years ago, so there were pioneers of this field like Bernd Dixon-Kosover, who's been heroically doing these computations for maybe 50 years. But then a lot more people joined this field, like myself, about 20 years ago, and that came with the twistor theory, twistor string theory. So the twistor space came about in December 2003 with Witten's paper called Perturbative Gauge Theory as a String Theory in Twistor Space. And in fact, on the front row, we have two of the organizers of the very first, Lionel and Scott, were the organizers of the very first meeting, which I really have very fond memories on nearby at Oxford, where this field really took off. And a nearby workshop happened shortly after, and it was called From Twistors to Amplitudes. So this is where this field really started. So let me just say maybe for 3 minutes about what exactly were the main ingredients. So what did Witten do? So amplitudes. So again, I'm going to be very, very schematic. Those who know. Those who haven't seen this, just to give you a vague idea. So amplitudes are usually, as when we study quantum field theory, amplitudes are usually thought of as a function of a momentum on a polarization. However, when we have a massless momentum, p square equals 0, we can write it as a product of two spinors, lambda and lambda tilde. So the amplitudes are characterized by just two spinors, lambda, lambda tilde, and a helicity plus or minus. So what Witten showed is that if you do have Fourier transform with respect to lambda tilde, then the amplitudes now live in twistor space in P3. And they have a very rich mathematical structure. And the statement is that if you have, an amplitude has a number of external legs n, and a number of negative helicity gluons, so number of, every leg could be plus or minus. So if the number of minuses is q, an amplitude has a q negative helicity gluons and n minus q positive helicity gluons, then in twistor space, the amplitude is 0 unless there exists a curve of degree q minus 1 passing through external points. So this is the very important observation that the amplitudes are supported on curves in twistor space. So this is the start of this field. So for example, at that time, there were certain examples of amplitudes known. So it was known that if at tree level, if all but two, if every outside external leg is a plus, or all pluses but one minus, the amplitude is 0, okay? Such amplitudes are 0. And why that is, because as I told you, the degree of the curve could be in this case, so Q is 0 or 1, so the degree of the curve is -1 or 0, there's no such curve. So it's a trivial statement that such amplitudes are 0. Then the simplest non-zero amplitude is the one with two negative helicity gluons. It's called MHV, and this will appear over and over, and it lies on a line on twistor space. So from this, I'm not going to review the twistor string theory, I'm just going to focus on amplitudes. From this construction, then Witten constructed the twistor string theory, which describes any, supposedly, this describes any tree-level gluon amplitudes, and in new ways of computing amplitudes emerge. So for example, as I told you, you have those curves in twistor space, and for example, if you have three negative helicity gluons, the degree of the curve, remember, was 2, and you can show that calculating amplitude reduces to solving an algebraic equation. On the other, so that was one way of computing it. The other way of computing, and that was completely new, and this is still mysterious why that is the case. And another way, a new way of computing amplitudes, which came from twistor string, was that this so-called expansion, you can compute an amplitude from those MHV amplitudes just from the line. So the construction, Witten constructed Witten twistor string, and new ways of computing amplitudes emerged, and new amplitudes were computed. And kind of the field evolved in two ways. On one hand, there was people computing amplitudes, but on the other hand, so since Lionel is chairing, I have to. The classic twistor people went on constructing various generalization of twistor strings. So, for example, you can find a nice. No, is this the nicest review of this all various ambitwistor strings? Would you say that's there are some others? So
not as recent.
Most recent, so there are others. Okay, so there was a parallel kind of development, so various twistor strings were constructed. But so for me, in this talk, I'll focus on what do we learn from the amplitude. So thanks to these developments, at tree level, very importantly, there exist several simple algorithms for computing any tree amplitude analytically, and these were these are now known as BCFW recursion relations. And for example, so before that, people were computing things with Feynman diagrams. So for example, if you are interested in 2 gluons going to 4 gluons, the 6-point amplitude, there are 220 Feynman diagrams. You would have some, but with the BCFW, there are only 2 terms, etc. So what I'm trying to illustrate to you is that the whole program undergoes this cycle. You find new structures. So in this particular case, this was inspired by twistor space and twistor string theory. then you use the structures and you develop new methods for the computations, and then you produce new calculations. So, and then you continue. The more, and this has been going on, I guess, for the past 20 years. So, tree amplitudes has been under complete control for 20 years. So, let me tell you a little bit about loop amplitude. So, at the wish list that I had, there are some processes, and there were like NLO, NNNLO. These are, N means next to leading order, that means a loop diagram. So, for example, when you study quantum field theory, you know, for example, this is the simplest integral you have to compute, and integrals, as you go to higher and higher loops, integrals get more and more complicated. So again, just a picture. So there's some complicated integrals, and then you get, when you start doing these, you get some special functions which grow, and I'll have more to say about this. Now, you might have heard, when talk about n equals 4, everybody immediately thinks of amplituhedron. So for the past 10 years, there's been also a geometric interpretation for the integrand of those amplitudes. So the subject of my talk is going to be the actual answer of the integrals. So you compute some loop amplitudes, you need to evaluate some complicated integral, but you have to do two things. First, you have to construct that integral that you have to evaluate, and then you have to evaluate it. So the amplituhedron that some of you might have heard about is about how do you write down the integrand, but you have to integrate it. So the talk that I'm giving today is because there's a lot of things one can talk about in n equals 4. My talk today is about the actual result of this integral. Okay, so good. Status of where do we stand in QCD? So this is, again, sure I'm omitting people, but I just took it from, it's a year old. I'm sure there's an update. I apologize for that. So where do we stand in, where are we at the QCD amplitudes? The state of the art is that the 4 gluon scattering has been computed up to 3 loops, and 5-point amplitudes have been computed to 2 loops, and all n are known numerical due to various packages. Okay, now that was part 1. I'm actually doing quite well on time. So hopefully I motivated for you the need for computing these amplitudes and explain to you what the status is. So for me, again, I come from string theory originally. This is hard. And in string theory, when it's hard, we try to find some toy model or do something simpler. So the part 2 of my talk is going to be about n equals to 4 Yang-Mills theory. So at the tree level, there's no distinction. At tree level, of course, non-supersymmetric theory amplitudes and supersymmetric theory amplitudes are the same, but at loop level, things are different, and n equals 4 is simpler. So why has n equals 4 attracted so much attention? So there's been a lot of work in the past 15 years. There's a lot of structure. There's extra symmetry. Oh, I'm also going to be talking, and I should have put it, about planar Yang-Mills. There's dual conformal symmetry. There's Youngian symmetry. There's connection to positive geometries. And I'm going to explain to you a little bit about cluster algebras, polytopes, and tropical geometry. And it's a simple model that likely can be solved exactly. And once we thought it would be done by now, but okay, still lots of work. But it's been the case that the tools we've been coming up with, the tools that we've developed over the years, such as the symbol, for example, that I will describe to you momentarily, have been very important for QCD. The tools and techniques have been applied to QCD. So it provides the general tools and intuition. So we have for the, still already 2 years old, so we have for this snow mass process, a lot of nice snow mass things. So with Nima, Dixon, MacLeod, Mark Spradl, and Yar Savchenko, we have a little review. So I refer you to this. So solving. So we want to solve n equals 4 Yang-Mills theory. Again, this is The origin is probably not our paper, but there's a nice picture I'd like to show. There's a threefold way to enlightenment in n equals 4. So number one, and that would be the subject of my talk, that's perturbative regime. So there's a perturbative gluons where we're talking about perturbative amplitudes. And here, this is just a summary of what I will say. There are bootstrap techniques where, making certain ansatzes and certain hypotheses about the singularity structures, we can make a lot of progress. And this review doesn't cover all the, there's been more development since then, but still, I think this is a good starting point. So there's a perturbative, I'll focus on this, but complementary approaches is the strong coupling. So via ADS CFT, the strong coupling is governed by some minimal surfaces in ADS. So starting with the work with Alda and Maldacena, there is a strong coupling story. And in parallel, there's an intermediate, a finite coupling story, mostly pursued by Basso, Sever, and Vieira, where certain techniques from integrability are being used. So there are these three kind of approaches to solving this problem of scattering in n equals 4 theory at different couplings. So let me just focus on the perturbative regime. Here's the status. Okay, so as I said, the amplitudes are characterized by three numbers. Number of points, so number of external legs, number of loops, and number of positive or negative helicity gluons. So that's MHV, N, MHV, N squared, MHV, etc. So this is an MHV, for example. So N, L, and K. So where do we stand? So the amplitudes for 4 and 5 points due to dual conformal symmetry are known to all loops due to the work of Baird, Dixon, and Smirnov from 20 years ago. Now, interesting things start appearing at 6 points, and so this is the result. The most recent result is 8 loop computations by Andy Liu and Lance Dixon. That's 2308. So if you start increasing the number of points, 7 points amplitudes are known up to 4 loops, and that's reviewed actually in this paper. So all n MHV amplitudes have been known also for a while. So now I'm increasing n. Now, and more recently, 8 and 9 MHV has been done by 3 loops by Song Hee and his students. Amusingly, the AI and machine learning is now being used by Lance Dixon and some of his postdocs, and also Kyle Kramer and others. So they've been using transformers to fit some of this high loop computation. So it's quite remarkable. And also I should mention, this didn't make it to my previous slide, an important, very important progress has been made recently in June. So actually there is an addition to this slide, and I just want to really highlight what's, because this is from June. So it turns out that for plane n equals 4 Yang-Mills theory, the amplitude could be written as a sum of just 3 integrals, okay? And these integrals, this has been known since Nima et al., Kani Hamed et al. Paper from maybe over 10 years ago, and it's been an outstanding problem to do these integrals. And so those folks, Anne Spearing, Matt Wilhelm, and Qi Zhang, recently were able to evaluate this integral exactly for any n. So this one they did maybe a year ago, and most recently, they have the all planar 2 loop amplitudes. So we've been trying to now understand what this implies for various things. So that's the status. Okay, very good. The status, methods. How has it been computing? So the pioneer and the Israeli Lance Dixon here, who's been pushing this program for the past 10 years, along with various collaborators. And so and this is really heroic computation. So they're computed via a bootstrap program. So where you do the following: you start with some ansatz, you write down an answer as a linear combination of functions, and then determine the coefficients by solving a large system of linear equations. And then you impose various constraints. Also, I should say, Andrew MacLeod has been absolutely, incredibly done important contribution to this. He's been the driving force in all of this. And you impose symmetry, you impose collinear limits, regiokinematics, et cetera, until the remarkable thing is that you get this very large system of equations, and then once you impose conditions, you get a unique answer. So it's quite remarkable. Okay, so, and you could say now, okay, very good, Bootstrap. Okay, maybe I heard about Bootstrap. Maybe some of you were not born during this. Okay, so it's not new. The idea of a bootstrap is not new, and it's been a goal of the in the 60s, there was something called an S-matrix program, where one tried to compute scattering amplitudes based on some physical principles and the understanding of the analytic structure. So there are two important ingredients that came into the game. And one I keep mentioning, and since it's Twistor conference, the absolutely crucial ingredient number one has been momentum twistors. So the variables in which all of these calculations are done are really momentum twistor variables. And none of that would have been possible without using those variables. And the other thing is also is something due to us, some statement about some, I will talk about something called sigmoid for these special functions. So let me just kind of give you a rough idea what these tools are. So you would think, as a mathematician especially, you just think of the amplitudes as a functions of some kinematics. And there are two things I have to explain to you. One is, what is the kinematics? What are the variables? And the other thing is, what are the functions? So the kinematics is described by these momentum twistors. This is really, due to Andrew Hodges, actually. Some of you might already know what these are. So as I said, the massless momenter, P, you can write down as a product of two spinors, lambda and lambda tilde. A labels the number of particles. Maybe that's not the best conventions. So then you can go to dual coordinates. From X, you go from P, you go to X. And then you introduce these momentum twistors Z, which live in P3 in twistor space by this formula. And everywhere on the next slides, in any paper you open in this field, you see those brackets. And these brackets, A, B, C, D, are nothing but this 4x4 determinant. So Z, the coordinates, so A, B, C, D, label the particles 1, 2, 3, 4, for example. And this is just a P3 index, so 1, 2, 3, 4. Okay, so and these Z's are functions on this Grassmannian GR4n. So the second thing I need to explain to you, so that's the variables. Instead of momentum, you have these brackets all over the place. And then you have the functions. And the functions, what are the functions? So the functions are a generalization of the log functions. So there's something special about n equals 4 Yang-Mills theory, is that at L loops, the functions appearing have uniform transcendentality. So for example, a one loop expression has transcendentality 2. Transcendentality is defined like pi has transcendentality 1, log is transcendentality 1. Transcendentality 2 would be pi squared, log squared, Li 2, etc., etc. So at L loops, the polylog functions, these are just generalizations of the log, start appearing. Then they're more in degree of complexity. There's generalized multi-polylog functions, or otherwise known also Goncharov polylogs, where I can sprinkle some numbers A's into those recursions, and then as you go higher, for example, for 2 loop 10 points n cubed MHV, there are elliptic polylogs appearing. So the state of the art, I actually just spent 2 weeks in Munich, where there's a whole now, so this amplitudes community now grew, and there's a sub-communities. There's a sub-community of folks, and they have been studying just this elliptic polylogs, and they have an annual conference called Elliptics, and this was like I think they said 8th meeting, so I was at the 8th meeting, and there were 90 people studying elliptic polylogs, and there's a lot of amazing results. So this would be a subject by itself. But these elliptic polylogs are absolutely crucial for anything. Anytime you need to do an integral in QCD, those appear. So I was just amazed and impressed that how this field grew. So these are the types of functions that appear.
Sorry, Anastasia,
Yeah.
really dumb question. Is it understood in n=4 when generically in perturbation?
Yes, that's when they start appearing.
Okay.
N10, L2, K3.
But so they never appear for n squared.
No. Yeah. So yeah, and then in fact now we have any n impressions, and they have exact expressions using the elliptic. So there's a whole generalization of how you think about symbol. What do you do? So that's that. So my talk mostly actually is going to be NMHV, MHV and MHV and NMHV, but those start appearing right here. Yeah, and again, that's just a huge field by itself. Okay, very good. So roughly I try to so far explain to you the amplitudes of some functions, these polylog functions, elliptic polylogs of some kinematics, and kinematics described by momentum twistors. So what another ingredient, remember right here, so this I kind of sketched, symbol. This is something that describes the singularity structure of those functions. So we don't want we don't want to know. So this is a think of it as a further simplification of a function. So and it encodes the location of singularities. So what's a symbol? The best thing to do is just to give you an example. So now I'm defining a symbol of a polylog function. If you've seen it, great. If you haven't, hopefully maybe you can learn. So define it as follows by example. Take a function log. The symbol of this function is x. Okay, postulate. Take a function Li2. The symbol of a function of this Li2 function is -1 minus x tensor x. And more general, any MHV and NMHV amplitudes can be expressed in terms of these generalized polylogs, which could be defined recursively. So if you have a weight m polylog, it's probably hard to see in the back. You can always write it as a function of degree m-1 d log of something. Okay, so for example, right here. So for example, take Li2. So d of Li2 could be written as, so that's just a definition, minus log 1 minus z d log z. So remember I told you the symbol of log z is just z, and then by this definition, symbol of Li2 is -1 minus z tensor z. Okay, so that at least maybe you can remember these two things, and then recursively you can continue, and that's defined for any multi-polylog functions. So why is the symbol useful? The symbol is useful because it completely trivializes the identities among those polylog functions. So for example, here you take an identity. You could take any of your favorite identities and apply the symbol operation to this. So Li2 of x is, as I taught you, -1 minus x tensor x. Li2 of minus x, I changed x to minus x, written here. Then there are very little properties you need to know, which follow from the definition. And you can rewrite this as minus, so remember identity, 1 minus x times 1 plus x is 1 minus x squared. And then this constant doesn't matter. So this is nothing but 1 minus x squared tensor x. Now, you can write, again, using properties that are trivial to derive, you can write this as a tensor product of x squared and put a half. And this is nothing but the symbol of Li2 of x squared. So it's a cute little, not little, this is little, but the functions become complicated, and it's a very useful tool to deal with identities among those polylog functions. And by now there are packages, for example, Claude Dour has a package that is widely used in QCD, simplifying their various expressions. So it's been very, very important. From now that I explained to you, there's amplitudes, it's a function of those kinematic variables, I will not be talking about the whole function. I'm just going to be talking about symbol. So when instead of talking about log, I will just be talking about x and things like that. So what do we know about the symbol of the alphabet for n equals 4 Yang-Mills amplitudes? Well, we've known a lot, and there's been a lot of interesting results. So since our paper, so the symbol for 6 and 7 points amplitudes is presented on this page, so it's been known for about 10 years. So as I promised you, there will be always brackets, and you know now what these brackets are. Okay, but now these brackets are not defined right here. Hopefully I define it on the next slide. So given the brackets, you can have various polynomial expressions of them. So that's what these are. So, and these are called, sometimes you hear letters. So we think of them as letters that appear in certain amplitudes. So these are all, for example, this is just a little survey. So for 6 points, we know there are 15 letters. There are 7 points, there are 49 letters, and these are known. For the 8-point symbol alphabet, it's been computed some time ago, it gets more complicated. And it's not just polynomials on those brackets, it involves square roots. So the alphabet is known up to 9 points. So this is, again, the work by Song-hee and some of his students. And it looks like this. Okay, it looks like a mess. So before I try to, so we want to look at some structures of this. Let me just say quickly, how were these derived? How did people compute these? So for 6 points, people did the integral, and the integral was like long expression, with Dilduka, and Smirnov about 15 years ago. And then with the help of symbol, this integrals was simplified. So this is how useful this symbol was. And it was just some Lie-4 of certain expressions. And then for higher points, again, maybe this is a little bit too technical, but I just want to emphasize over and over again that this is just not some results I'm just flipping, but there's a lot of hard work, something called Q-bar equation, and that relates the L loop amplitudes to L-1 amplitude, and it's been starting from Simon Caron-Rouault to most recent the work by Song-hee's and students. So that's how these results were obtained. So this is just a result. And now what we would like to do is we want to ask a question: is there a description of these symbol letters? How do you understand this? Can you write them down? Is there structure? Because if we want to solve eventually n equals 4, we'd like to have some understanding. We don't want to just have a formula. And it's been a lot of, so this could be probably a lecture course by now. So there's been a lot of development in mathematics. So it turns out that for 6 and 7 points, the alphabet is described by cluster algebras. However, for 8 and 9 points, these are called so-called Grassmannian cluster algebras. But the Grassmannian cluster algebras become infinite at 8 points and higher. So there's been many approaches to understand those. It's literally just these 2 slides. You can just, now I've defined for you the brackets. You can take this list, and you can just, as a mathematician, you can ask a question. Okay, how do I understand what structures? Can I have an independent derivation or understanding of this? So there's been a tropical geometry pursued by James Drummond, Omer Gurdargan, Yorgos Papathanasiou. There's a dual understanding by Thomas Lam and Nimar Kani-Hamed. There's so we did with actually who's here, who used to be at Brown, try to understand this from Plaby graphs. There's an approach from tensor diagrams, also something used in mathematics. So it's kind of cool because you first study some mathematics and it becomes very, very useful for the descriptions. Aidan Herdershi, who's now a postdoc at the IAS, had a scattering diagrams approach. And there's also been some work from understanding these from Schubert problem. So this is just to emphasize there's been work, and it's slower, it's slow progress, but they're really deep mathematics. Now I am going to so again, I've given many talks on some of this, but today I'm going to tell you more recent. Before I do that, before I turn to physics, I'm going to talk about the number 1, which is cluster algebras. Since I mentioned this, actually I do have I have 10 minutes.
So you've got a countdown up there which says 20.
Oh, 20. Okay, so then I could. So for 6 and 7, this simple letters that I've described, I've written before, could be understood as a Grassmannian, cluster coordinates of Grassmannian cluster algebra. So if you know cluster algebra, is great. If you don't, now's the time to maybe pay attention. The A2 cluster algebra could be understood, defined as follows. You take a quiver with the 2, so think a diagram for A2, and arrows like that. You have coordinates A1 and A2, and you define a mutation rule in this manner. And then if you continue on, you see that it stops. And these are the only cluster coordinates for A2. Now, what is GR? I told you the Grassmannian relevant cluster algebra is GR for n, GR for 6. It turns out the initial quiver is that of A3, so ignore the boxes. It just I'm not good with figures, so I just screenshot them from papers, and I have younger people doing the figures. I apologize. So this is A3, and then if you mutate, then you get. So right here you've got only 5 of this. You get 15 cluster coordinates, and then so that's an independent definition, right? So you produce the list, and it matches the list I showed you. So right here. Right, this one. So that was quite amazing because it came from a completely different approach, mathematics. So cluster algebra by now is a subject in itself. There are classes taught in universities on that. So for 7 points, it's GR for 7. It turns out that it's E6. So that's the so 2 by 3 quiver that is drawn is mutation equivalent to actually E6. I should have drawn it. I didn't. So, and the number of quivers start growing. It's 833 quivers. And if you write down all your cluster coordinates, that would be exactly the alphabet that you saw in the previous transparency. So good. So that's at least I explained to you the bullet point number 1. Now, why it is important. So these are these letters are the input serve as an input into the Bootstrap program. So the way Bootstrap program that computes, for example, for 6 and 7 points amplitudes to high loops, is you start with those letters and then you pose the various conditions. So we've been, for a long time, wanted to understand and have a derivation of, so we have data, right? We have data for 2 loops, and then there's a bootstrap ansatz, and people bootstrap it. But we would like to eventually have a proof that there's no other letters, for example. So, and that's what I call symbol alphabet from physics. And that would be, let me just, again, I'm good that I have 17 minutes, sufficient. So I'm going to get a little bit more technical now and describe some of the ways to describe this alphabet. So this is the work actually from a year ago with so Mark Spradlin and then a former student Luc Lipster, who is now in Edinburgh, and Akshay Lishpustrikant, who is now in Oxford, and they graduated. So we have a unwritten policy: when people graduate and leave, they should move on to different things. So you can ask why no progress in a year. So it took us a while to train this new student, and he's making progress. So first I'll describe what's in this paper, and then I just say quickly what He-Cheng Wang has been doing. Okay, so we want to learn, we want to have a proof. We want to have provided a foundation for the Amplitudes Bootstrap program. We want to have a derivation of the letters that I've described to you. And there's been some well-known ways to do this, and and there's been known in physics for many years, so this is back to physics, that Landau singularities describe the singularity structures of amplitudes. So if you have a Feynman integral, you could write down Landau equations for that integral, so okay, these are the equations. So maybe I'll have an example on the next slide. So if you have an integral like that, Landau equations are that those internal propagators satisfy this condition, and then you have something like Kirchhoff condition. So alpha are the Feynman parameters, and so given an integral, this set of equations called Landau equations, and singularities occur when the equations have solutions. So for example, if you look at this system of equations, you can quickly convince yourself that this is a solution when the following is true. And this is written in terms of momentum twistors is something like that. And indeed, that's a singularity structure of the integral. So there's a very well-known techniques. And there's been a lot of, I mean, we've worked in it. First, 10 years ago, we started looking at Landau equations for plane integrals for integrals, but there's a revival of interest because Mizera and Tellon and others had algebraic geometry approach to solving these equations. They have a code, for example, recent code. So there's been a revival of interest in the Landau equations. In general, in fact, in April, there was even a conference on just Landau equations in Edinburgh. So, very good. So, what do we want to do? We want to do something specific. So it turns out so Mark and his students observed the following, that for any n particle amplitude in any massless planar theory, they conjectured that the Landau singularities are a subset of those of a special type of ziggurat graphs. What's a ziggurat graph? The word ziggurat, you can Google, comes from those structures in ancient Mesopotamia. So what is a ziggurat graph? So you start with, so the white points and white, these are not, if you're familiar with on-shell diagrams, nothing to do with that. These are just, the white dots means external link, so this is actually a 4-point diagram, and they go by 2. So from this, you can take this box and add a structure here. So like you see, you start here and you start a ziggurat. And then you start with this one and you add a structure. So these are special types of ziggurat graphs. So there was a work by this mathematician who showed that any graph in massless theory can be reduced to a ziggurat by a sequence of moves like this. And they observed that for 6 points, that Landau equations are invariant under such moves. So by this, it looks like you can just start with ziggurat graphs and compute their Landau singularities, okay? Which is pretty cool, because these are simpler things to compute. So for example, okay, so this is a 6-point graph, and then you can do this y delta. This is like an ENM. These are y delta moves. Again, I don't want to go into these details, but you can do this, and for 6 points that matches, and so you do this move, you only have one graph to compute, you compute the Landau singularities of this, and then that matches the 6-point symbol letters that I showed. So, which is pretty cool, because that maybe one can go and prove this to all orders. So that's what, in fact, this was started by, we made a poor student, Luke, do this. So we started, so let's do 7 points. So for 7 points, you start with ziggurat, and then you do the sequence of moves, and you reduce it to this graph, and all you have to do is to compute Landau singularities of this. And we were starting to find interesting things. We were finding agreements. So we found all but 7 letters. So then Akshay joined, and then we looked at this leading Landau singularity is sub-leading Landau singularity, so one of the alphas is 0. And then, so we were short by 7, and then we started redoing, and there were extras. So we were finding basically, 14 extra letters, and they were appearing in these graphs. So it's a nice but very technical exercise. So this is just to prove that the work was done by Duke and Akshay. So it would be interesting. So of course these are individual graphs. So what to do? So do we find a contradiction? Do we take it seriously, or do we just call it a day and move on? I think it would be, I mean, it's an interesting, we would approve at the end of the day. It would be interesting to see if these extra letters appear in higher loops. I should also mention this actually, that I'm a little bit cheating. There was a little bit, I'm cheating, but just, there are some solutions violating the equivalence, but I'm not gonna go to these details. Nevertheless, I think it's an interesting exercise to see if there's a unique solution to the bootstrap program with these extra letters that we've been finding, and that's what our new student has been doing. So he, along the way, he learned very quickly, all of the Bootstrap program. And so probably he'll find 0, but it would be spectacular if he finds a solution with those. So you start with extra letters, and if he finds a solution, I think that would be probably not, but I think it would be interesting. So again, all of this is a step towards trying to understand better and better the singularity structure and what is the input into the Bootstrap program. Okay, so I'm going to conclude. I'm going to finish early. If you ask questions. So the conclusion is that hopefully I gave you an overview that n equals 4 Yang-Mills amplitudes have been computed to the very high order. So for 6 points up to 8 loops, 7 points up to 4 loops. And this was done via the Dixon and MacLeod Bootstrap program. Now the input into the Bootstrap program are the letters, the simple alphabet letters. And it's very important to understand the origin of these letters. And indeed, this is not just for n equals 4. It's very, very important. And so we've started exploring this. And at the end of the day, the future is bright, I think. There are a lot more to do. So, NLK. You want to go to all high N, high L, beyond polylogs, beyond planar, and beyond n equals 4. And with that, I stop. Thank you.
Thanks very much. So with the zigzag graph, so there's the square block graphs. Is there an assumption that they generate all the symbol letters, or is it just those were easy ones to look at?
No, easy. I don't know if actually it's easy. I wouldn't use the word easy, but any graph can be reduced. So there's so this came about. In fact, this was any graph can be reduced to zigzag and this is an obscure math thesis by this person, and I think students actually found it by Googling a few years ago. So that's the origin of this.
Okay.
And this move, and then for 6 points, it's indeed Landau equations are invariant under these moves. But
so zigzag graphs are a normal form that you can go to, and then if you can classify all of those, then you can get everything.
Hopefully, yeah, that's the idea, yeah.
On that topic, I think I'm right in saying that those moves come from the Reidemeister moves of the corresponding knot diagram. Does that make it better or worse?
I think it would be interesting to explore. These moves also appear like in Y delta in the NM, yeah. But for knots, I think this might be something interesting to say, yeah.
Okay.
Yeah, that's just that basically came about as an observation, yeah. But maybe there's some connection, yeah.
That relationship would stop if you then move out of the planar case.
Yeah, everything I have to say, yeah, this is crucially planar, absolutely. But I think what you mentioned might be interesting to understand better, yeah.
Proposing a link to knot theory.
You're proposing a link to knot theory, I think. Yes.
Oh yeah.
So could you emphasize what of these achievements were about planar diagrams?
Everything I talked about was planar. However, there's a lot of progress on non-planar. In particular, people who compute, you might have heard about supergravity computations, and it's very important to do non-planar. There are techniques. So my talk was about planar, but there are techniques and there are lots of developments in that area too. For example, just 2 weeks ago, I think Zwiebern and Radu had a paper on better understanding of non-planar, yeah. The techniques and BCJA is important. Yeah, there's a whole community so people doing gravity, that's what, they absolutely need non-planar, but my talk, what I do is planar.
And another thing, can you include masses in this story?
Can I do massive?
Masses, yeah.
Yeah, masses, can we do masses? So, in this story, this is a big story. There are a lot of things. For example, symbol, yes, there are some techniques. And in particular, for example, solving Landau equations, Misera and Tellen, that's massive. So lots of things. So when you say this story, you have to be specific which story. So what part, I said so many things. So Yeah, so yes, massive integrals are very, very important, and people certainly look at them. However, for this program, the momentum twistors and twistors, this is all massless. So everything I talked about today had those brackets, had momentum twistors. That's all mass. This is where this is absolutely crucial. And momentum twistors also very important to be planar because you have that dual conformal symmetry. So these are two assumptions, two reasons why we love n equals 4.
So twistors don't work beyond planar?
Well, this is the question too. I mean,
well, momentum twist.
Momentum
I mean, there are plenty of twistors, twister ways of doing amplitudes that are non-planar.
Yeah.
But momentum twistors.
Momentum twistors are
tend
very
to be tied into the planar story. But I guess the color kinematics people know how to move from planar to non-planar as well.
The whom?
The color kinematics people.
Yeah, the BCJ. Yeah. So
the JJ.
BCJ. Yeah.
So.
Yeah, but for me, absolutely important. All of this story high loops, absolutely crucial. The masslessness. Yeah.
Sorry, maybe just to piggyback on that, like, wouldn't it be the case that if you went to the Coulomb branch, say?
Oh yeah, there are some. Yeah, thank you. There is some work. Mark has been working with Johannes Henn for maybe 10 years. There's some ways using different regularization. Yeah, there is work there too, but that's not what I cover. Yeah, that's absolutely correct. There's some papers.
If you low supersymmetry, like n equal 2, for example.
Low supersymmetry. So symbol has been applied. I'm very proud of that to QCD and real amplitude. So I'm thrilled with that. So if you low supersymmetry, what exactly? What part of the story? Yeah, people, I guess, maybe not so much. For example, in ABGM, there's but that's 3D. So there are other theories other than n equals 4 that people look at. I think there's some maybe papers with less supersymmetry in 4D, but for example, for 3D ABGM, some of that, there's been like amplitude story, there's amplitude story, so that's, for example, there is a story, yes.
Can you briefly summarize what's been understood about the symbols application into just ordinary QCD?
Yes, I don't have the slide. Some 3-loop computations have been. So Tancredi would be the name, Thomas German, this would be the name, Ein and Gardi. So basically, anytime, so the reason it's been done is because anytime you need to do the integral, it's polylogs, and they're complicated. So, and people, there were techniques to simplify those expressions, but nowadays, all of these simplifications are done with a symbol. And then I guess the thing is now the polylog tools code by Claude Dour. And that's been basically all over the place. That's a standard code that people use now, and that gives you a symbol, etc. Yeah.
Is kind of the main structural difference that just there's not a uniform transcendentality at L loops in?
Yeah, you basically split the QCD into pieces. That's what, and then plus, of course, as you know, there's also rational pieces, as you very well know. So. Yes, so you split it into parts, and that's how you simplify how they simplify the expressions. Yeah, that's vaguely.
But also, like in QCD, isn't the main application to like soft anomalous dimension rather than an S?
No, but you still have to evaluate integrals. So this meeting I went to, this elliptics, it's all about doing the integrals, and there's a lot. Yeah, I guess Tancredi would be the name that most. Young person, you have to compute those integrals. You can't avoid it. So I mean,
I would imagine that for the lower order ones, I mean the 2-loop stuff. You're not seeing elliptics there. You said.
Yeah. But I showed you the. Yeah. But for QCD, the integrals, the state of the art, which is again I took it from last year's amplitudes, are those, and that's the Abreu also, Chicherian. These are. There's also some 2-loop. We heard that some 2-loop 6 points integrals. So these are the ones to evaluate. Yeah.
So if there are no further questions, there are drinks waiting for us outside. So let's thank Anastasia again.